Hello and welcome to another episode of the Fully Charged Show podcast. Every now and then, it's so hard to start these introductions because there's such a thrill for me to talk to some of the people that I've been able to talk to on this show, and this one is really right up there. This is amazing. So I would think probably, well, I thought it was 2011. It's actually 2012. I watched a TED talk by Professor Donald Sadoway about energy storage and about batteries and about battery chemistry. And I was absolutely gripped by it, partly because of his explanation of the actual technology, but partly because of his bigger vision of why that could be quite an important topic. And it's taken until 2023 to get to talk to him on the Fully Charged Show podcast. So he is an extraordinary man. I'm going to read you out the description of his work from the Massachusetts Institute of Technology website, which is where he lectures and is a professor, MIT, as it's more commonly known, where, to be honest, when you look at incredible technological breakthroughs of the last, let's not exaggerate, 45 years, a huge number of them have either come out of MIT or been inspired or come out of people who've been to MIT. It's kind of become a pretty extraordinary place for innovation, science, and technology. So Professor David Sadoway's research seeks to establish the scientific underpinnings for technologies that make efficient use of energy and natural resources in an environmentally sound manner. That is fascinating. So I'm not even going to begin to describe a liquid metal battery, but that is what he's worked on for a long time, but that is what is about to be installed. And I'll let Donald explain that. But he's a fascinating man, and I think you'll really enjoy listening to him. He's a genuine pioneer in this field with an incredibly realistic and occasionally very challenging grasp of the technologies that we deal with on the Fully Charged Show and that I effectively been promoting on the Fully Charged Show. And I'm not going to back down from any of that, but it's quite good to have some of your assumptions and your assumptions challenged by someone who, not some troll on Twitter, but someone who actually knows how these things work, who's worked on them for decades. Fascinating, real privilege. Please welcome to the Fully Charged Show podcast, Professor Donald Sadoway. So, Donald, thank you very, very much for joining us today. It's a real privilege to be able to talk to you. Your take on battery chemistry, I think, is the thing that I'm really fascinated by, what you've been developing, what you've been working on for the last, I don't want to know how many years, quite a long time. And because at the moment it's a really pertinent topic, is so much misinformation, particularly in this country at the moment, going around about batteries and what batteries do and whether we can use them and whether they're reliable. All those, you will be aware of them, I'm sure, all the negative press they get. And so it's quite useful to have someone who actually knows what a battery is, how it works, how they're developing. So one of the things, kind of first thing I wanted to ask you, because I remember watching your TED talk from, I think, 2011. So that I can't work
2012.
2012. So 11 years ago. So in that time, in my understanding of battery technology, there have been some quite big advances. But could you give a little précis of what's been going on in the battery industry and with the different battery chemistries that have appeared in that period, in that time?
Well, I'm always a bit of a contrarian, and so I would dispute that a lot of things have happened.
Right.
There's to your earlier comments, there is a lot of misinformation, disinformation, and in point of fact, if you take a look at automotive applications or even handheld devices, we're still running the tired 30-year-old lithium-ion technology.
Right.
There have been some improvements in manufacturing. That's true.
Right.
The composition of the electrodes in the lithium-ion battery is essentially unchanged. Nickel oxide, manganese oxide, cobalt oxide. And then again, John Goodenough came with the lithium iron phosphate. That was in the early 90s. But we've heard some prattle about solid state batteries, which I think is nonsense.
Right. Oh, right.
But we don't see them.
Yeah. No, we haven't seen them
Wearing
yet. No.
lithium metal batteries, but there's nothing in the market that's running lithium metal, and we can get into why that's the case. There are scientific reasons why. So I don't see anything new in handheld. And then for massive stationary storage, I invented liquid metal battery at Ambry, which is the company that I founded with two of my students. It's now, 2023, and only now are they in a position to release the first product into customer hands.
Right.
And it's been a very, very arduous journey because in spite of market needs, with intermittent renewables, you have to have storage to bridge the gap when the sun doesn't shine. But the industry is very risk averse, and has not embraced the technologies. They've foolishly been installing lithium ion chemistry in massive 100, 200 megawatt hour installations with the disastrous results. Just think about Moss Landing in California, fire resulting closure in the Pacific Coast Highway. There are some people out there advocating flow batteries, metal air batteries. These are, hydrogen. I mean, these are all different variations of nonsense. And so, it's the green transition is more easily spoken of than
than actually achieved. Yes.
So I know that's a long answer to your question, but
no, it's good.
I just wanted to make sure that my position was that in point of fact, I don't see a lot of innovation in the battery arena.
So, I mean, I suppose
what kinds of publications? Okay, so I know that the universities and the paper mills are working, but when it comes to commerce, my mantra has always been science, and I even say this in the TED Talk back in 2012: science in service of society.
Yeah,
not science in service of career building. And if it's science in service of society, it has to get into commerce. Yeah, and that's why I agreed with my two students, Louis Ortiz and David Bradwell, to found the Liquid Metal Battery Corporation, which we ultimately renamed Ambry. It was easier to pronounce and to remember. And so it was about getting the liquid metal battery so as to be commercially available. Otherwise, remain on the lab bench. Paper in Nature is fantastic for the career, but it doesn't change society.
It doesn't change society. And also, I mean, that's the one thing I've learned from, being a casual observer of the battery research and development industry. And I've been to Oxford University in this country, in Birmingham University, where they're doing a lot of research into tiny variations in lithium-ion battery chemistry. Yeah. But the one thing I've learned is the difference between a watch-sized battery in a laboratory and 100 kilowatt-hour battery in a car is enormous. Oh. And I am utterly unable to judge from seeing sort of early versions of batteries, which is clearly where I love your strident comments about that, because I can't tell. I'm always assumed that one of those batteries might work. Yeah. But I wouldn't be able to tell which one, and there's so far, none of them have.
Yeah. Well, there's the reduction of practice at the laboratory bench. But then in order to get to commerce, you have to be able to reproduce that at scale. Yeah. And as you rightly point out, say the 100 kilowatt hour pack that goes into an automobile, the amount of engineering and know-how that goes into that is just staggering.
Yeah.
And then what we faced with Ambry was we had to invent the entire universe, because there was no firm could manufacture liquid metal batteries at scale, in spite of all of the remarkable progress. And I will be the first to state that the lithium-ion battery has become so much cheaper because of advances in manufacturing. The chemistry has remained largely unchanged. And people got better and better at manufacturing and reliably, and so on and so forth. But all of that was inapplicable to liquid metal battery chemistry because the form factor is different, the operating temperature, the chemistry, everything. There was almost nothing that we could transfer. And so we had to invent the machinery because there wasn't even machinery.
There's no machinery to make it. Yeah.
And I'm an electrochemist. I'm not a mechanical engineer. And there are no mechanical engineers. You can't get on your computer and dial in liquidmetalbatterymanufacturing.com. There is no such website. So we had to invent everything. Inventmeauniverse.com. That's what I needed.
Yeah. But then can you explain, so for the people who won't have heard of liquid metal batteries, the two things. One, because I know I'm just trying to think of the level that we can pitch this at.
Well, I can describe it.
If you can describe it and I can understand it, then any of our audience can understand it. So, but how it works, but then also what its applications are.
Okay, so liquid metal battery was invented for stationary storage at massive scale. So that meant I totally took off the table the concerns about mobility. Yeah. One of my statements is, don't pay for attributes you don't need. It's stupid to put a lithium-ion battery in a massive stationary application because it's not going to move. So why pay for mobility? It'll be like paying for a telephone that you can carry, but you intend to always have it at your desk. Well, what are you paying for? Miniaturization. So what do? We looked at, because it wasn't going to move, we didn't have to restrict to room temperature operation because you're not going to be putting it up against your face or putting it on your lap. So that freed us. And we ended up choosing a battery that had all liquids. So the electrodes are liquid and the electrolyte is liquid. But the electrodes are metals and they operate at elevated temperature, typically around 500 degrees Celsius.
Right. Oh,
well,
right.
500 degrees Celsius, you're not going to be able to use an aqueous electrolyte or an organic electrolyte, similar to what is used in the lithium-ion battery. Well, I had a deep knowledge of electrometallurgy when it comes to metals extraction: aluminum, magnesium, alkali metals, lithium, sodium. So I resorted to molten salt. So instead of dissolving salt in water, we take something that's a cousin of table salt, and we go up to a temperature at which it melts, and you end up with a clear, colorless liquid. There it is. Right. And the thing is that the liquid metal is insoluble in the molten salt, and the molten salt is insoluble in the liquid metal. So when you put these things together, you have three layers, and they stratify like as salad oil and vinegar.
Yeah. So there's no physical barrier between them. They literally separate.
There's no membranes. Right. So imagine instead of salad oil and vinegar, which is two layers, imagine you had yet a third layer. Yeah. So you got the salad oil is floating on top of the vinegar, and then imagine you had yet another layer beneath that. And so the way the battery operates is the way every other battery does. In the lithium-ion battery on discharge, the lithium inside the graphite goes into solution and then moves over to the positive electrode, and the same thing happens here. Only the liquid metal on the top, that becomes the negative. It dissolves into the molten salt as ions, and then gradually the liquid metal from the negative electrode, which some people mistakenly call the anode eventually becomes thinner and thinner, and the cathode layer on the bottom becomes deeper and deeper. Wow. And then finally, you get the current going through the external circuit. And the other feature here is, because it's operating at elevated temperature, as the current passes, we all know how our laptops heat up, how our phones heat up with the current passing. Well, that's a threat in a lithium-ion battery. For
Yeah.
us, it's a feature because we
Right.
want to keep the battery at temperature. So when the battery discharges, the current flowing generates heat, and we trap that heat. And then when we charge the battery, we force current through it, and then electro-refine the metal of the negative electrode out of the bottom of the cell and put it back up at the top. And again, generate heat. And so you can imagine a duty cycle where we discharge it over, 5 or 6 hours, let it idle for 5 or 6 hours, then charge it over 5 or 6 hours. And this daily cycle of discharge and charge with appropriate insulation at massive scale is self-heating. There's no external heaters, and there's no danger of thermal runaway. So it's safe. Nothing in the battery is flammable. And it's dirt cheap. So
because that's
what's not to like?
Yes.
It's a brand new technology, and everybody's wondering if the thing will really work.
Yeah.
In a risk-averse, capital-intensive sector of the economy, nobody wants to be first adopter.
Right.
Everyone wants to be first to be second. Well, when Microsoft announced earlier this year that they will be the first purchaser of liquid metal battery, now this has generated a good deal of interest, and now the order book is filling, and so on. But it's been a long journey.
Yeah. And I mean, I can't help wondering, because this is the kind of genius of it, was there ever a precursor to it of a slightly different? Because I have never heard of this notion before, or that it came from anyone else. Because no, I never have. I mean, was there anything at all remotely like it that was, in existence 50 years ago or 20 years ago? I don't know. I mean, it just...
Yeah, you're right. Well, actually, there was. There had been some work at Argonne National Laboratory here in the United States. They were working on, because there was the molten salt breeder reactor and then the liquid metal breeder reactor. So there was a lot of work with molten salts and liquid metals. And there was some work that resulted in the formation of a sodium bismuth battery that had molten salt in it. But sodium, unfortunately, is unacceptably soluble in the molten salt. So even though this device would work, it wouldn't be able to hold the charge really well. But there was some very nice work done by people at Argonne Labs, and but at that time electricity was so cheap, and this was all related to nuclear power and so on. There was no interest. Just as the sodium sulfur battery was invented at the Ford Motor Company in 1968.
Right. Wow.
And yet the gasoline was 25 cents a gallon.
So
Nobody cared about electric cars. So there were some gestures, but they never gained any traction.
Yeah.
And I didn't, quite frankly, I was unaware of that literature. I started working on this around 2005, and then somewhere along the way I came upon it, and I reached out to a man by the name of Elton Cairns. And he was one of the researchers there, and he ultimately became a professor of chemical engineering at UC Berkeley. And I reached out to him, and he came to MIT and spent several days with my students and postdocs, and we learned a lot from him about pitfalls, because we only hear about successes, we never hear about failures.
Yes. Yeah.
So then we're doomed to repeat those failures. But Elton was really gracious, and we learned a lot from him.
Right.
And I think he was an ardent fan of mine.
Right.
Because I was now taking another run at this.
Yeah.
We changed the chemistry a lot. There's no sodium, no business. But what we have now is a calcium antimony battery. We'll see where it goes.
Yeah. But I mean, that's a critical thing that is clearly becoming a big issue at the moment, is the materials that are used in that. But so all the materials that you're using in that that battery are common and not contentious. I mean, I'm asking that. I mean, because there's clearly a lot of leverage against batteries from that standpoint.
Yeah, well, there's no question they have to be ethically sourced. That we don't want to
Yeah,
have, cobalt, which they call it the blood red metal. Even
yeah,
though cobalt oxide, when you dope it into glass, you get the beautiful cobalt blue.
yes,
But
yeah.
because of the way it's being
Extracted. Yeah,
extracted, there are ethical questions there. Nickel mining,
yeah,
big issue. People are talking about going after the seabed to get manganese
yeah.
nodules. I mean, none of this stuff is, without damage
No,
to the environment. That it is intended to be climate change mitigation technology, which
yes,
is attacking the environment. It's
yeah,
you have to break the egg to make the omelet. So,
yeah. Well, that's someone said to me recently. No, there's nothing that we don't grow or dig up. And when you go, that can't be right. And then you go through everything you've ever experienced in your life, and you go, dug up, grown, dug up, grown.
yeah,
Does seem to be the way we do
it
it.
comes from mining or agriculture.
Yeah, yeah,
And you can even say polymers. Polymers are derived from petroleum. So petroleum has two product streams. One is fuels, and the other is petrochemicals, which is not just lubricants. It's the precursor to polymers. So the cellophane wrapping and so on, all of that stuff started as
I've always argued that the oil industry is critically important for the human race. I just want to burn less of it. There's so many other uses, but it's very, very difficult.
Look, I will even contend that. I think you can burn it. You have to be able to burn it in such a way that there are no CO2 emissions. You want the thermal value, but you don't want the CO2 emissions. And everybody has the simple-minded approach. Well, if we don't want CO2 emissions, we must prohibit burning. Well, that's one way. You could shut down all industry, and that would limit CO2 as well. But I think that might be socially unacceptable.
I think there may be some kickback. Yeah,
there might be some pushback. So, but yeah, I guess we're digressing. We were talking.
Yeah, we are a bit. Yes, but I mean that is. But what I'm excited to see then is what your company actually produces for Microsoft. I mean, in terms of its storage capacity, would you say that has the potential to be much bigger than anything we've seen from billions of Tesla batteries in boxes in the desert?
Well, if you're willing to spend the money and put more and more Tesla batteries together, you can achieve whatever total capacity you wish. The difference is that with those say hundreds of megawatt hour installations in the desert, about 40% of your stored energy is going to power the air conditioning to keep those batteries from overheating. Because lithium ion, if the batteries get up, you can pick a number, probably somewhere around 60 degrees Celsius, then the battery becomes unstable and could ultimately catch fire and so on.
Right.
Whereas the liquid metal, if you want to put 200, 400, 500 megawatt hour installation in the desert, no problem. Because they're operating at 500. They don't care if the desert's 50 degrees Celsius. It doesn't care. It's self-heating. It doesn't care. There's no thermal runaway. So, you can do. This is the pernicious aspect of the lithium-ion cell, is that you can make it work, but at what price? That because people, if I told you I can give you carbon-free electricity from solar cells for say 5 cents a kilowatt hour, but when I store it so as to allow you to have continuous uninterrupted electricity from sunset to sunrise, the cost of doing so will now raise the price of electricity from 5 cents a kilowatt hour to 25 cents a kilowatt hour. You'd say, well, wait a minute, why is it costing so much? Well, it's the capital cost plus the operating cost, plus you're spending half of your charge to keep the battery from catching fire. So the thing is, it has to be sustainability and profitable sustainability. If sustainability, if the green transition means green impoverishment, I don't think you're going to get a lot of fans from that.
No. going to get the old pushback again, which we're getting at the moment
Yeah.
in this country, big time. But then, so that is an area of the battery industry that I do understand. The energy losses of maintaining those battery packs at a safe operating temperature. I know that used a lot of energy, but with a liquid metal battery, presumably, is there a point, like when you first switch them on, when they're first connected, is they presumably then require quite a lot of energy to get them up to that temperature? I can understand once they're at that temperature, then the actual, what is the energy consumption of the batteries apart from storing it and returning it?
So the round trip efficiency is 80%.
Wow. Okay.
80. So that means about 20% of the energy is being converted into joule heat, desirably so.
Yeah.
And so people say, wow, lithium ion is da-da-da. These are beauty contest numbers.
Yeah.
It doesn't matter whether the round trip efficiency is 97% or 80%. The only metric that counts when it comes to this stationary storage is dollars per kilowatt hour per cycle.
Yeah. And you can do that cheaper.
Lithium fails because of the high capital cost, high operating cost, and the fade rate. We all know from our phones and from our laptops.
Yeah.
On day one, we're so excited, brand new unit, device. And after about 2 years, we find that it doesn't get us through the day the way it did on day one, because there's less and less capacity to store the charge. It's natural degradation. The liquid metal battery, we've got data on cells that have been running deep discharge, full discharge every day. In some cases, we do multiple times a day to build up the number of cycles. After 5,000 cycles and say 4 years operating temperature, they're still retaining 99+% of nameplate capacity. So I'm going to beat you on dollars per kilowatt hour per cycle. If I showed you a battery that had a measly 20% round trip efficiency and a capital cost of $5 per kilowatt hour, you'd buy it.
You'd still do it, yeah.
Because the other is just, it's going to cause the ratepayer to see, he's going to be cross-eyed when he gets the bill.
Yes. But then, so that tell me about the first installation then, because what are Microsoft using it for? Because is that for like data centers, or is it what are they? Why do they want batteries?
You're spot on. That's it exactly.
Right.
The data centers are gigantic consumers of electricity, and they want to have their data centers 100% green.
Right.
So that means either wind or solar, and you can't have a data center that operates part-time. Yeah. So they need a reliable bridge technology, and I think this is a testimony, because this isn't done with government funding or subsidies or anything like that. And they're Microsoft. They could have chosen any technology. Yeah. They did not choose lithium ion. They did not choose aqueous flow batteries. They did not choose metal air batteries. They chose liquid metal.
Well, they didn't choose hydrogen as well, which I just wanted, because I know you mentioned that.
That's another.
Yeah, I don't want to go. It's just I only mention it because I would say it's maybe 10 times a day I'll get a tweet that just says, what are you going on about all these batteries for? Hydrogen is the future. There's no other explanation. It's just that. And I'm always happy. I go, please, let hydrogen be the future. Don't let me stop you.
Well, it always will be the future, I guess.
Yeah, yes, unfortunately, it does seem to be that. But then, because I was going to ask you about vanadium flow batteries, because I have a friend who's involved in that. I don't need to ask you about that, because that's, he's got a lot of vanadium flow batteries at his farm, and they work. But I don't know, and they, in that sense, the difference between them and lithium ion is they benefit from being completely discharged and recharged. That seems to be, which is, I think, critically important for static big storage.
Yes.
You do not want them to fade, and you want to be able to use all the capacity they have. That's kind of which you can't in lithium ion. Everybody knows that. I mean, that's
so the only thing I would say that makes me shy away from vanadium or any of the other aqueous flow batteries is that they operate with water, and aqueous electrochemistry is more limited than molten salt electrochemistry. So I was looking for something that had a little wider voltage window and things like this.
Right.
But they do work, and but ultimately, when you start thinking about dollars per kilowatt hour per cycle, as water doesn't spontaneously flow, so they hit bumps.
That needs to be pumped. Yes,
and the pumps have to be working. If the pump stops working, then the ability to generate electricity goes way down, because you've got stagnant water, and the concentration of vanadium in water is comparatively dilute. So it is thanks to the forced convection by the pumping that gives you the illusion of more ions per unit time going past the electrode. And it works. It works. But, you've got moving parts. There's going to be some maintenance. You've got a lot of connections, a lot of, how many kilometers of piping and so on and so forth. It will work. And, for the farm installation, it's far more sensible than lithium ion.
Yeah. But then, so the liquid metal battery is would that be in a kind of essentially a contained sealed unit that has no pipes or pumps, doesn't need them. It does it anyway within that unit. Is that a way of thinking about it?
The customer wants a box with two terminals, one with the right side and one with the minus side. They don't care what's inside. They're going to be hamsters running around inside. They don't care. They just want the electricity to come out on demand. So the liquid metal battery really starts to come into its own. If it's too small, it won't generate enough heat. So you can't have a 10 kilowatt hour, 15 kilowatt hour. It really starts to feel good at around 10 megawatt hours. And so these 100 megawatt hour things, you're looking at shipping containers. And they're cool to the touch on the outside. And as you say, you don't see any piping or anything. You just see this big terminal plus sign and minus.
Big box. Plus and minus.
Plus, better be at least one of each polarity. You can have more than one plus, more than one minus, but you can't have no minuses. All pluses, no.
Yeah.
You won't get a circuit,
Right, yeah. But then, so there's that's one of the fascinating things about it, is that there's quite a lot of talk. We've come across it here where energy storage systems that produce heat, like lithium ion batteries, in a colder climate, like we have in the UK, there's talk of taking that heat and using it for district heating things. But there's not, you wouldn't want to take away the heat in your batteries. You want to hold on to that heat, I'm assuming.
That's correct. Yeah.
So there's which also reduces the need for pipes and things.
Now, some people have asked me, there are these devices that can operate by using a temperature differential to generate electricity.
Right.
But again, they're really. You can even have a refrigerator that operates by the passage of electric current and causes a metal plate to cool and so on. But you're talking about NASA price point things.
And one of the things that's come up recently and it's one of those popular topics that people will bandy around the terms without, I think, possibly knowing what it means. Because you did mention solid state batteries. We've had a lot of contentious discussions around Toyota and their fluctuating attitude to electric vehicles. They seem to have decided now that they're going to go for electric vehicles, but they're going to be solid state batteries and they're going to be better than anyone else's. I noticed you were quite dismissive. I have no opinion or vested interest in one way or the other, but you didn't seem terribly enthusiastic about solid state batteries.
Well, I've worked on that. I built a solid state lithium metal battery back in 1997.
Right.
And but it was too far ahead of its time. It was dismissed as pointless because the conductivity in the solid, in this case, it was a polymer. So we had lithium metal. The polymer was both the separator and the electrolyte, non-flammable. And then on the other side, we had cobalt oxide or manganese oxide or some such thing. The conductivity is lower. And when I read these press releases or pieces written by journalists who clearly do not have enough of the scientific background, that they've taken some copy that was given to them by some promoter of said technology. They say that with the solid state, it'll be safer and it'll operate at higher charge and discharge rates than the conventional. That's not true. The conductivity of lithium ion in the liquid is higher than that in the solid. And plus, everything that I've heard, people are talking about using either solid oxides like lithium, lanthanum, zirconium oxide. And think about how cheap that's going to be. Or there's an argyrodite, which has got sulfur, fluorine, phosphorus, and it's a very complex solid, and it's not pliable, the way I had the polymer. And then the interface, because now you have lithium metal, solid metal. And then you've got a solid, let's go back to the lithium, lanthanum, zircon. You call it LLZO. I guess you call it LLZ. All right. Yeah. So I grew up in Canada, so I know I'm a little bit bilingual.
Yes, I can tell.
I'm like Snit. So if you've got the interface between the ceramic electrolyte and the solid metal, it's not a perfect mating, because the liquid can just splash up against the metal electrode or whatever the electrode is. But now you've got this little bit of a gap there. And then the same thing on the other side. Let's say you're using nickel, manganese, cobalt oxide for the positive electrode. And now you've got the LLZO, and that interface is it's not a perfect mesh. And so now if you look carefully, I've caught somebody from QuantumScape saying that, well, actually, we do use just a little bit of liquid. They put a little bit of liquid at the interface. And so what do you mean? You're using liquid. And so the all-solid-state battery, the ASSB now means almost solid-state battery. It's not all solid-state battery.
Right.
So, I don't care. It's not a crime. But just this whole business, I mean, there's the sense of trying to get rid of the volatile, flammable electrolyte, that's correct.
Right.
But then to say, well, it must be solid, well, that's one answer. That would be like saying we're going to prevent burning of all fossil fuels so as to prevent all CO2 emissions. Well, what if you were able to destroy CO2 before it went up this flue? Right. Then you could burn without, there are some people talking about carbon capture and things like this. So anyways, for me, the all-solid-state battery, which we don't have any evidence of it in commerce, it's sort of, it sounds good, but, as speaking as someone who's worked with these things, when I hear about ceramic electrolyte, and this is going to be a monolith, it's going to be a ceramic spacer that's both the spacer and the solid electrolyte. Ceramics are fragile and they're brittle. And this is one of the fallacies that I've seen over the years, material science, where a material scientist will make a discovery of a material that has remarkably improved performance in this one property. So let's say I've seen people talk about back in the 80s, there was a discovery of conducting polymers, and some polymers, conjugated polymers, can be made to conduct electricity.
Right.
And these people came out and they said, wow, this is the end of copper. I mean, you can conduct and so on. But it's true that if you do the calculations, you get really good, because the polymer typically has a density not too different from water, whereas copper has a density of about 8. So, per unit mass, the polymer looks really attractive. Again, I've never seen anybody move the the copper wiring in the walls of my house. So I don't know why having them low mass is an advantage. But anyways, so but these polymers are fragile,
Right.
and they're subject to attack by humidity and so on. If you point all this out, the guys say, "Oh, I know, but it's early stage. You'll see." But it's been over 40 years, but I don't see any people making cables that are going to conduct electricity out of these conjugated polymers. Fantastic discovery, have use in things like sensors and so on and so forth. But same as, why am I diverging on this path? Because the same thing is happening with this solid state battery conversation. They say,
Right.
well, we've got solid, it's got very high conductivity, and it's not flammable, and it's this, but it's fragile and it's brittle, and the interfaces are high impedance, and they just go, oh, Sadoway, you're such a negatron. Why can't you imagine things are going to get better in the future? I'm saying, you can't just wish these things away.
Yeah. No, it's kind of hard science. It's difficult. I mean, because I'm intrigued to find out your opinion of if there are battery-based solutions that you can see for transport, for mobile use. I mean, I don't know what your best bet is, or is there any hope of a kind of next generation of, even if it is lithium ion with cobalt in it or whatever else? I mean, obviously, so I want to talk briefly about fires, but let's do that a bit later on. But I mean, if there's obviously enormous pressure to come up with this. I mean, there must be a lot of investment in battery research and developing different battery technologies around the world. There's got to be it's become a thing.
So, I think we have to get beyond lithium.
Right.
Again, as I said in a TED Talk, you want to make some dirt cheap, you make it out of dirt.
Yeah.
Preferably dirt that's locally sourced. We learn one thing from COVID, which is supply chains, globalization. These are not such good ideas.
Sustainable things, yeah.
Because, you start getting into geopolitics, all of a sudden you discover that you might have some trouble acquiring some of these materials. And you can't build a car missing one part. It has to have everything. And so it just has one part missing. So I continue to work on new battery chemistries, nothing to do with lithium, nothing to do with volatile flammable organics. So if I had that battery ready to go, I wouldn't be taking part in this interview. I'd be lying back in a swimming pool with a cocktail in my hand,
counting your money.
Going flat. Well, I'd be but it's not there yet. But I still think that there are some viable, potentially viable, and by viable I mean economically viable. Because I could build you a gorgeous battery out of lithium and tellurium or something like this, but I mean it's going to come in at the NASA price point. You're not going to put cars on the road at a NASA price point. Right now, we don't see widespread adoption of electric vehicles, even in spite of the heavy subsidies that are being offered here in the United States. People aren't buying them because the price point is still too high. I mean, we've never been asked to pay more for less. When the mobile phone came, it was expensive, but people said the price-performance ratio is correct. I can do so much more with this phone. And then came the smartphone. It's not just a phone. It's a wholesale communication device. I can send text. I can receive data. I can see streaming video. I can do so many things with this thing. I hold it in my hand, and I'll pay. There were no subsidies for that. An electric car comes along, and it costs way more. It drives less far. You talk about cold. I'm living in Boston. I grew up in Toronto. And, in the Canadian winter,
it's cold.
This car is, if it's parked outside. So we haven't solved all those problems.
Yeah.
And the price point is so much higher than that of a regular internal combustion engine vehicle. So what's the reason? When you buy a new car, an electric vehicle, you are essentially buying a battery.
Yeah.
And it comes with a little bit of coach work. The coach work is like, it's added on.
Yeah.
But you're buying a battery, 100 kilowatt hour battery at, what is it? It's $100 a kilowatt hour.
Yeah.
I mean, you're buying the battery,
Yeah.
the chassis, and then the joystick and blah, blah, blah. This is just like, throw it in. So, we want to get widespread adoption of electric vehicles. We got to get the price of the battery down.
Yeah.
Although the alternative is to put less battery. Instead of
Well,
only
that's quite a big
kilowatt
argument.
hours.
Yeah. Yeah.
And now you have an even shorter driving range, and the distance between. This is why hydrogen vehicles didn't catch on, because, I mean, we don't have enough electric charging points.
Yeah.
But with hydrogen, it was even fewer.
Yeah.
I mean, no one's going to have a vehicle that they can't refuel, or that the trip is always planned so as to be tethered to the refueling stop.
Yeah.
And that's not acceptable. So I continue to imagine the unimaginable,
Right.
and keep me in your Rolodex there, and
Yes.
call me back and see if I've had any luck.
Because it is that. I mean, it is the only argument I would have. It's not against what you said, but the sort of observation is, because I've had electric cars for a long time, so now 13, nearly 14 years, and all I can remember is the cost per kilowatt hour when I got my Nissan Leaf was about $1,200, $1,300 a kilowatt hour.
Yeah.
And now, as you say, it's around about 100. It's actually about 110, I think, is the average price per kilowatt hour, which is a pretty remarkable drop in that period of time. But but what you're talking about, what we really need to be able to do is get that cost down to sort of sub $50 a kilowatt hour. And then you're talking about, you have a 30, 40, 50 kilowatt hour battery that costs probably the same as building an engine, because building engines is, it's a huge and complex topic, which I've been involved in discussing with many people. But the way that the business works now, the automotive industry, is by effectively selling you the car a petrol car or diesel car really cheap, a gasoline car, because they know there's an income after it, because to keep it going, you've got to have all those spare parts, which is the big challenge with electric vehicles. I've had electric cars long enough to know they don't need an oil change and a new fan belt and a new radiator hose, and they don't need anything. They're very cheap to run, but I absolutely agree, and it's a critically important point, is they're just too expensive to buy new. And I think you're absolutely right. I never bought new cars when I was young because I didn't have any money. So buying a new car is still, to me, why would you do it? I want a third-hand one that's a bit worn out.
Yeah. So you can buy a used car if it's a internal combustion engine.
Yeah.
Because you can fix it up and this, that.
Yeah.
But when you're buying a used electric vehicle, you're buying a used battery.
Yeah.
You don't know how it's performed. You don't know what its condition is, and so you're really buying a lottery ticket, because if that battery is in bad condition, it's not like replacing the fan belt. This is an off-body restoration. You've got, because for safety reasons, that battery is buried deep inside, so that if you're in a minor collision, you want to protect that battery case with all of the cells, so that if that case is deformed just a little bit at one edge, and some of those cells are crimped and short, a fire will start, and then it will spread without boundary, and at that point you've got a major fire.
Yeah.
And so, as a result, being able to change that battery, if it comes to needing to do so, that's not a simple matter.
No. But I mean, do you think then that the battery electric vehicle is by default just the concept of it? Even if you could build a battery that you drive the car into a wall at 200 miles an hour, it still doesn't catch fire. I mean, you're dead, but the car doesn't catch fire. If you could develop technology like that, do you still think the notion of it is wrong or bound to fail?
No, I mean,
Right.
I've got several battery chemistries right now that I'm working on that are completely non-flammable.
Right.
So you don't worry about catching fire as a result of even a minor collision.
Right.
Minor collision where there's some deformation and it causes just a tiny bit of crimping at one edge of because the battery is ultimately in this gigantic box.
Yeah.
And if one corner of that box is dented, like a dented can in a supermarket, then that could be the beginning of a chain reaction for lithium ion. The remedy is to have a battery that has nothing flammable.
Yeah.
But right now we're so enamored of the lithium ion chemistry, and if you speak to the people who are the inventors of it, and the first adopter was Sony. Sony gave us the lithium.
Yeah.
It didn't come from the battery industry. The legacy industry was making nickel metal hydride, and they refused to manufacture lithium ion.
Right.
And Sony brought it, but for what? Yeah. Not for cars. They brought it for handheld devices, for the Walkman, for a little radio, and then for the
video cameras, whatever.
The handy cam, the very first camera that had both the optics and the recording medium inside the one box. That's why it was called the handy cam, because before my children were small, I had a video camera that had the transport with the video cassette. It was probably a VHS cassette.
Would have been.
That was big. And then that was just the transport. The battery was in another box that went
with a wire.
Me. Yeah. And it was heavy. And after all of that, I might get 60 minutes of runtime.
Just about, yeah.
And Sony brought this out. But then when people decided that they were going to launch the all-electric vehicle with this thing, there were many people in the industry were horrified, saying that this thing isn't safe at that cell size. Batteries. So this is not the cell; it's the
combined batteries.
We're putting some tens of kilowatt hours under the seat. I drove an electric car in 1994. It was at Ford Motor Company, and it was being powered by sodium sulfur batteries.
Right.
And those things were running at 325 degrees Celsius.
Wow.
And it was fantastic. That's what got me working on batteries. Until then, I was working exclusively on electrometallurgy, aluminum, easy, and so on. And I took a ride in that, and I thought, wow, this is fantastic. Acceleration is neck snapping from 0 to 30, neck snapping from, this is in miles per hour, from 50 to 70 miles per hour. Again, neck snapping, because the torque curve of an electric motor is flat. Yeah. Whereas internal combustion engine, as you go to higher and higher velocities, it will take you higher, but acceleration is off, reduced. And I said, the only reason we have this electric car is we need a better battery.
Yeah.
That's what got me working on it.
Yeah.
I didn't do it because I wanted to help foster the green transition. I did it because
there wasn't one back then anyway.
There wasn't one, 1994. But I did like neck snapping acceleration. The fact that we're at zero tailpipe emissions, I thought, well, that's in the would be nice category. It was not mandatory for me at that time.
Yeah. But I suppose essentially, because I don't want to take up any more of your time, but it's been amazing talking to you. But I suppose I'm searching rather hopelessly for a little bit of optimism in the future of ground transportation, because I am now seeing things like 60, 70, 90 ton trucks with battery packs that they swap out. I've seen this in Australia, and there's a lot of it happening, I know, in America with the batteries are effectively getting bigger and bigger. I've just seen a big earth moving machine built by Volvo that has a 450 kilowatt hour battery at the back of it. I mean, it's a really big one. It's the sort of thing you'd build a highway with. It's not the thing you'd dig out some foundations for your shed. It's massive.
Look, I'm all in favor of intensive electrification and deep decarbonization.
Right.
And I would love to see that go forward. But whether it's a 450 kilowatt hour battery or 200 kilowatt hour battery, I would feel a lot better if I knew that it weren't a lithium ion chemistry.
Right.
The notion of 450 kilowatt hours under one roof, and you got lithium ion, it gives me pause.
Yeah. And this, I mean, so that main reservation with that is the fire risk, is the fact that it's flammable. Yeah. So that's really the challenge. Then maybe isn't, but it's the flammability and the cost. It's those two things, I guess, are the two.
Well, the cost, of course, but some people are willing to pay for, if a mining company buys this Volvo tool and is able to say that we are sustainably digging the dirt out of the ground, it's worth it. And there are cost reductions. I've been to a mine where we were probably down 1.5 kilometers below ground, and all of the
it's all electric anyway.
Is diesel, and so they have gigantic fans because they have to remove the emissions because there's carbon monoxide, there's particulates, and so on, and you'll kill everybody in the mine. Yeah. And so, if you had all electric vehicles, it simplifies so much.
Yeah.
And you don't go very far. It's not as though,
you're not doing long journeys.
Miles on a single charge. You're going to go down 1.5 kilometers and back.
Yeah.
And then you charge it once you get to the top and so on. Really, the 450 is basically to give you a huge ballast so that you can have the power that you need.
Yeah.
But that's fantastic.
Yeah. Donald, it's been amazing. I've got a whole long list of other questions I wanted to ask you, but we've done nearly an hour. You've been amazing to give us this time. That's been a real pleasure to talk to you. Now, please do come on the show again. It would be great to have you again. Well, I really hope you enjoyed that. I must admit, I know that I forgot to say, do subscribe and tell your friends and all those things. So I'm saying that now. Do subscribe and tell your friends. The podcasts are doing really well, and there's loads of people listening to them and watching them, and it's very fulfilling. And please do say to people, if you want to find out about what is really going on in this world, watch the Fully Charged Show podcast. We definitely want to get Professor Sadoway back on the show at some point. There are some exciting things that he's working on now that he doesn't want to talk about now, which is absolutely understandable. We'll see as over the next months and years what occurs. But I'm very keen to try and do an episode once they have produced and installed them, the batteries he was talking about with Microsoft. Really interesting stuff, because that's what we call game-changing technology. Amazing. Anyway, that's all. As always, if you have been, thank you for watching / listening.